Hello and welcome to this lecture. In this lecture, we will look at what are called confidence intervals. Okay, this is a slightly different approach to doing estimation, one can say. So far we saw problems which are called point estimation problems. So you're given an unknown parameter, give me one value for that unknown parameter. So in some cases, maybe that's not what you're interested in. In some cases, you're interested in an interval. Okay, can you give an interval and say, I don't know the exact value of my uh, unknown parameter, but I know that it lies inside this interval. Okay, so that's the sort of thing that's done in confidence intervals. Okay, where do you see confidence intervals most of the time? Most of the time, you see them in surveys and results. Okay, so today the world is full of surveys. Okay, so many opinion polls here and there. People ask questions about whether you like this, whether you don't like this, and then they claim one conclusion. Here is one conclusion that you will find in a Gallup survey. Gallup is a pretty famous surveying organization. You find it in a website. It says 82% of Indians are willing to take the COVID-19 vaccine. Okay, so how did they come up with this statement? They asked 3,045 people, they claim in their data, from the time period November 24th to Jan 8th, November 24th of 2020 to Jan 8th of 2021. So many languages were used in querying people. They were called on the mobile phone and asked whether or not they'll take vaccines. And 95%, look at this number is what I'm most interested in. What does this mean? So this 82%, they claim from the survey, they have 95% confidence level in that 82%, and the margin of error is 3%. Okay, so what does this mean? It's not, if you've not seen it before, it's not clear what it means. So any good survey will give this information. Okay, so take it from me, if this information is not there, if how many people participated in it, what is the demographics of the people, how they were asked, and 95% confidence level and margin of error, if this information is not there, do not trust the survey. Okay, that survey has not been done properly, or at least the results are not being communicated to you properly. Any proper survey has to share how many people responded, who are the people who responded, and these two numbers. One is called confidence level, the other is called margin of error. Okay, why are these things important? Because there can be other surveys. Here is another survey. This is through another app called Local Circles. You can go on their website, you can find this survey as well. It says 40% Indians willing to take vaccine. So this was done Jan 25, 2021, sort of around the same period. And this is through an app. It's a mobile app that people have to install if they want to. And they claim there were 9,628 votes. And the demographics is people from 299 districts, so many people from tier 1 cities, so many people from tier 2, so many people rural, etc. This is the information they give. They don't give confidence level, they don't give margin of error. They've not put that down. I would have liked it if they had put that down, but they've not put down. But look at the huge difference in the result put out by two different surveys. Okay, 82% says one, 40% says the other. Okay, something has to be wrong, and this is January of 2021. I don't know. You know how India was at this time, so you can imagine what you trust more, right? So how many, whether you trust 80% more or 40% more, you can decide for yourself. But this is the kind of thing you'll see. So you'll see many people put out survey results like this without any data on how they got the survey. They'll just say 60% people believe, 70% people believe. They'll not give you the information on how they came to that conclusion. So you have to look for that information definitely, and you have to look for these two words. I mean, these levels, actually good surveys will give these levels. They'll give you this confidence level, margin of error. What do they mean? Are they related to estimation in some way? It turns out yes. And in this lecture, we'll quickly see what these numbers mean and how they calculate. So all of these are tied around estimation of sample mean. Okay, and this is something called confidence interval. Okay, so here is a typical problem. X1 through Xn is IID according to X, and I'm interested in estimating the parameter mu equals expected value of X. It's some, I mean, I keep saying parameter. It's, you have to think of it as some property of the underlying distribution, which is the mean. Okay, so mu equals expected value of X. A very common estimator is the sample mean. Okay, and we will stick to that. We'll take sample mean as the estimator. It's a good estimator. It's an ML estimator, it's an MME estimator, every estimator that you can think of. So it's a good estimator for the mean. Okay, supposing somebody tells you, see, remember mu hat is a random variable, right? So mu hat is a random variable, and expected value of mu hat equals mu. Okay, all these things we know. Suppose somebody tells you probability that absolute value of mu hat, okay, again if you want to picture this event, you can draw the line and then this mu and this mu minus 0.03 and then mu plus 0.03 in this interval. Okay. The probability that mu hat lies in this interval is 0.95. With probability 0.95. That is what this statement means. Probability that absolute value of mu hat minus mu is less than 0.03 is 0.95. Okay. So, I have written that out, it lies in this interval mu hat. So you can sort of twist this around and also say mu lies in the interval mu hat minus 0.03, mu hat plus 0.03 with probability 0.95. So, it is possible. So, mu hat you can take as a particular sample value. So, this is this is mu hat in one sampling instance, and you can say it lies in minus 0.03 plus 0.03 with 95% probability. The technical words that people would use to describe the situation is this one sampling instance. You take one sampling instance, so supposing in one sampling instance you got a value of mu hat, some value 10, 20, whatever, some value of mu hat you got. You can put out that value and say this is the estimate of the sample mean at a margin of error 3% and confidence level 95%. How did I get 3 and 95? It is because of this statement. Okay, probability that mu hat minus mu is within 0.03 is at least 0.95. So, that is the meaning of this confidence interval statement. So, you can see I have 95% confidence that I am within 0.03 of the number I am putting out. Okay, so, I got some samples, I calculated the sample mean, and what is my confidence level? 95% confidence level, I have that the actual answer is within 0.03. That is the sort of statement one is making when they say confidence level and margin of error. So, let us generalize this a little bit. In general, if you can somehow prove that probability that mod mu hat minus mu less than alpha equals beta, and alpha you are imagining is a small fraction and beta is a large fraction, then if you compute mu hat in one sampling instance, somebody gives you the actual samples, you compute the mu hat, then you say that mu hat is an estimate of the sample mean with the margin of error 100 alpha percent at confidence level 100 beta percent. Okay, so, you multiply beta by 100 and say percent, alpha by 100 and say percent. Okay, so, this is the definition for mu and for margin of error and confidence level. Okay, hopefully it is clear. Confidence level is the probability with which that you are inside that interval, and margin of error is the width of the interval, sort of how much it deviates from mu on both sides. Okay. So, how do you find this alpha and beta? Okay, so x is some distribution given to you, it has a CDF fx. Supposing this is known, distribution of x is known, maybe this CDF of x is known. Okay. So, we know probability that x is less than or equal to small x is the CDF evaluated at x, standard definition. And what about this probability that absolute value of x minus mu is less than alpha? It turns out you can compute it using the CDF. Okay, this is not very hard. This is the probability that x is between mu minus alpha and mu plus alpha. Remember, it is continuous, so less than or equal to, all of these are the same. So, this is the CDF evaluated at mu plus alpha minus CDF evaluated at mu minus alpha. Okay. So, this so this guy is the actual expression for this probability. Now, if you want this to be equal to beta, what will alpha be? Okay. So, again imagine this is mu and you are going to this interval mu minus alpha, mu plus alpha, okay, and there is a probability with which mu hat will x will fall inside this interval. As you keep increasing alpha, that probability will only increase. If alpha is 0, this probability will be 0, right? This is equal to 0 if alpha is 0, and increases with alpha. It will strictly increase with alpha. And as alpha goes to infinity, it will go to 1. Okay? So this function will go from 0 to 1 as alpha goes from 0 to infinity. Okay? So any beta you put to, you will get a unique value for alpha. Right? So you keep increasing alpha till you hit the probability of beta. Okay? You will get different probabilities for different alpha. You keep changing alpha. When you hit 0.95 or the value of beta that you want, you stop. That's your alpha. Okay? So that's what's going on here. Okay? So it's a pictorial representation and the function here. Okay? So sometimes you will have symmetry. If you have symmetry, then probability on the left side is equal to probability on the right side, and you can simplify your calculation a little bit. I'm not going to detail there, it's not so important. Okay. So the most common case is normal samples. You assume your samples are normal mu sigma squared, and sigma square is known. Okay. So you know the variance, you don't know the mean. Okay. So this is an assumption that one can make. We'll relax the knowing the variance soon enough, but as of now, let's say you have normal samples with mean mu, which is unknown, and variance sigma square, which is known. Okay, so mu is unknown. Okay, so what is my goal? I want to calculate these confidence levels, or confidence levels and margin of error. At what margin of error? What confidence level? I want to calculate it for normal samples. Why normal? You can say a lot of things, but in fact, normal is a very common distribution because of the CLT and all that, right? So that's why normal is the first thing we look at. So the estimator is the sample mean. Notice the sequence of arguments actually very simple. Mu hat, right, which is the sample mean. What is the distribution of that? It is again normal. We know it's normal with mean mu and variance sigma square by n. Okay, so this is very important. This variance sigma square by n is important. You can prove this for mu hat. It's going to be normal with mean mu and variance sigma square by n. This is one of the properties of the Gaussian distribution, right? It's a very interesting property. So what I do here is centralize and normalize this distribution. How do I centralize? I subtract the mean, divide by the standard deviation. Okay, so it's square root of sigma square by n is sigma by root n. So this is what I'm going to call as some z. Okay, so some z. And this guy has a normal 0, 1 distribution. Okay, so this is a very standard random variable, and its CDF is well known. Okay, so there are tables which will give you the CDF of normal 0, 1. There are computation packages will definitely give you the CDF. Okay. Now, why is this important? Because if you see probability that mu hat minus mu is less than alpha is equal to beta, you can divide both sides by sigma by root n. Okay. If you divide both sides by sigma by root n, on the left side you have mu hat minus mu divided by sigma by root n, and then on the right hand side you have alpha by sigma by root n. So this is not changing anything, right? The inequality, I am dividing both sides by a positive quantity, so it does not change anything. So this probability, this equation is the same as this equation. Okay, but on the other hand, this guy is normal, right? So this is the same as probability that a normal 0, 1 distribution is less than something. Okay, so we all know the normal 0, 1 distribution, right? So it looks something like this. Okay, and you're going to look at this point and this point, and say this is alpha by sigma by root n. This is minus alpha by sigma by root n. Okay, and this area is beta. Okay, as you vary beta, this area will keep increasing, right? Now it turns out if this quantity alpha by sigma by root n, if it is 0.99, then you get beta as 0.68. If it is 1.64, you get beta 0.9. If it is 1.96, you get a beta of 0.95. Okay, so this comes from, this is calculated using CDF of standard normal. Okay. So this is how a typical confidence level calculation will go for normal samples. Okay, when the variance is known. Okay, so it's very easy to look at it. You just centralize, move it around, and then from this table you look up a 95% confidence level. This factor alpha by sigma by root n becomes 1.96. So how do you use this to find confidence level? Here's a concrete example. I have given 16 samples drawn from a normal distribution with mean unknown and sigma equals 3. We have to find out a 95% confidence interval for mu. How do you find that? First, n is 16. You find the sample mean, it's 10.06 and sigma is 3. So 95% confidence interval, so beta is 0.95. And using the CDF of normal 0, 1, we get alpha by sigma by root n is 1.96. So alpha is 1.96 times 3, sigma is 3, divided by root 16, that's 4, you can calculate, you get 1.47. So probability that mu hat minus mu is less than 1.47 is 0.95, right? So that's the calculation. Right? So this is what is the calculation. So 95% confidence interval is 10.06. Remember, this is 10 point, mu hat ended up being 10.06, right? So 10.06 minus 1.47, 10.06 plus 1.47, which is 8.59, 11.53. So what does this mean? Let me repeat once again what this means. This means that if you were to repeat the sampling more and more and more, once more, you keep repeating the sampling. This is one set of 16 samples, right? Take another set of 16 samples, you compute mu. Another set of 16 samples, you compute mu hat. Another set of 16 samples, you compute mu hat. You keep on getting that, right? That sample is more or less going to be within this window for with good probability 0.95. So about 95% of the time you will get values within this. Okay, so that is, I mean, it's sort of like something you can show roughly to be true. So the other way to think about it is the actual distribution mean is within this most of the times. Okay, so that's, it's sort of, it's difficult to imagine what that means, right? So normally people are not interested in that. Why would I get more and more and more samples? I have this sample, you tell me what it is what people would ask. But those are difficult kind of questions to answer, right? So this is the sort of guarantee that one can give. If you were to keep doing this sampling over and over and over again, 95% of the time, your your distribution will be within a within this window. What you get will be within this window. That's a reasonably confident statement you can make about this normal sample. So this is how you find the confidence interval. So this is how you do that calculation. Okay. Okay. So let's keep pushing ahead. So there is this other situation where you may not know sigma. Okay, so far we have looked at a situation where the standard deviation is known, the variance is known. We were able to quickly use the normal standard normal tables and do the calculation. What if it is not known? Okay, if it is not known, you have to do something called the t distribution. You have to use something called the t distribution. It's a slightly subtle thing. So let me just go through the calculation. Okay, so you have n random samples, mean mu and variance sigma squared. You have the sample mean, which is x bar 1 by n summation xi. And then you have the sample variance. This time I will use the 1 by n minus 1, right? So this s squared is 1 by n minus 1. It's that compensated n minus 1 to get unbiased estimate of the sample. So expected value of s squared is sigma squared. Right? So summation of xi minus x bar whole square. Okay. So we know some things about the distribution of these things, right? X bar is normal, 0 mean. Oh, it's not 0, it's actually mu. Sorry about that. X bar is normal with mean mu and variance sigma squared by n, and then n minus 1 s squared by sigma squared is chi squared n minus 1. So this is results we have seen before, not too much emphasis, but we have seen this before, and x bar and s are independent. Okay. So here is a very, very critical piece of critical result, which we have not seen before so far, but this is very useful in the context of confidence intervals. Okay. So x bar minus mu by sigma by root n, when you know sigma, is normal 0, 1. We used it before. When you don't know sigma, what are you going to do? You're going to estimate sigma, right? How do you estimate sigma? S. You have s square, and then s is going to be your estimate of sigma, square root of the sample variance, right? So now it turns out, if you do this calculation, x bar minus mu by s by root n instead of sigma by root n, remember if sigma is known and precise, it becomes normal. If sigma is not known and it is s, you are estimating it from the data, then you get a t distribution. You don't quite get a normal distribution. Okay. So x bar minus mu by sigma by root n is the standard normal. It looks something like this. This guy is a t distribution. Okay. How does the t distribution look? It looks like this. Okay. So, the t distribution will go, this is normal. The t distribution will generally look a little bit more spread out like this. This would be like t. Something like this you can sort of expect. Okay, it will sort of tend to that, as it depends on n. As n goes up, it will tend to that, but otherwise it will be a little bit more spread out than the normal distribution. Okay, so this Tn is a distribution, and you can assume that the CDF of Tn is known. Okay, the computer packages will give you that. Just like the normal CDF is known, CDF of Tn can also be assumed to be known in calculations. So, notice the subtle difference here, this x bar minus mu by sigma by root n. When you know sigma, when sigma is a constant, is normal. When you do not know sigma, you are estimating it from the sample variance, it becomes some other distribution called the t distribution. Okay. So, this is where the t distribution comes, t distribution with n minus 1 degrees of freedom. Okay. So, let us not try to understand this too much, I do not want to emphasize all the calculations and all that, but just how you go about doing normal samples with unknown variance. How do you do confidence intervals, right? So, this is something that can happen a lot. You will have samples, you want to assume it is normal, but then you will not know the variance. What do you do when you do not know the variance, right? So, you can find this first moment, second moment and all that, like this you can do, right. So, you have a particular sample instance x1 through xn, you can estimate a mean and a variance. You have an x bar, you have a sigma bar, sigma cap squared, right. So, you can estimate this. This is just sample mean, sample variance. Okay, I can go ahead and estimate this. Now, mu hat, right, which is my mu hat, remember mu hat is just x1 plus xn by n, right. This is mu hat. Mu hat I know is normal with mean mu and variance sigma squared by n. Okay. And the z, which is mu hat minus mu by s by root n. What is s? S again we defined before, right. So, I do not want to write the s definition again, it is the sample variance, right. S by root n is going to be t n minus 1, I know this. Okay. So, if I were to do probability that mu hat minus mu is less than alpha as beta, this is approximately the same as dividing this quantity. Remember, on the left hand side I am dividing by s by root n, right hand side I am going to define by sigma hat by root n. Okay. So, these two are not the very same quantities. This is a particular instance thing, this is actually a random variable, but because of weak law of large numbers and all that, we can expect these two to be approximately the same. Okay. So, this is the little trick that you use. If you know sigma, you divide by sigma by root n, that is great. If you do not know sigma, you want to divide by the sample standard deviation. When you divide by the sample standard deviation, you cannot be very sure, it is just approximate, but you can do something like this. Okay. So, probability that mu hat minus mu by s by root n is less than alpha by sigma hat by root n, this is beta, and then this guy is the tn minus 1 distribution. So, probability that absolute value of tn minus 1 is less than alpha by sigma root n. So, this you can solve using CDF of Tn minus 1. What do I mean by solve? Given beta, find alpha by sigma hat by root n. Okay, you can do this. The same, we did the same thing with normal 0 1. Now we are doing with Tn minus 1. That is the difference. Okay. So, let us repeat this for the same normal samples we had before. This is the same set of normal samples we had. Mu is unknown, sigma is unknown. How do you find 95% confidence interval for mu? How can you give an interval in which you can be sure that 95% of the time, in some sense, in this repeated sampling sense, your mu will lie. Okay. So, let us compute. N is 16. I am computing the sample mean here. I am adding up all of them, dividing by 16. I got 10.06. I am computing the sample standard deviation, that comes to 3.297 for this samples. Okay, you can repeat this, you can take these numbers and do the calculation yourself. If beta is 0.95, you can use the CDF of T15, right, Tn minus 1, you will get alpha by sigma hat by root n to be 2.13. Okay, so this is again the same calculation, except that the CDF is different, it is not normal 0 1, it is this T distribution. Okay, so from here you can calculate alpha to be 1.76, and then you know that this is approximately 0.95, and you can put out a 95% confidence interval and a margin of error. What is the error, etc. you can put up. Okay. So, this is how confidence interval calculations are done. A very natural question is, what if samples are not normal? You simply assume it is normal. some samples need not be normal, at least even the sample mean is going to be normal. You have CLT and all that, right? So there's good assumption there. And then if the specific distribution is known, you can do better bounds. So for instance, a very common set of situations is Bernoulli P samples. So this is what happens in sampling surveys, right? You sample and ask either yes or no question. Are you going to take a vaccine or not, right? Yes or no. So it's only Bernoulli P answer, right? Yes or no. So the sample variance will be P times 1 minus P by N. And it turns out you can upper bound it at 0.25. So this has a maximum value at P equals half. Okay, so you can check that out. It's a quadratic. You can see it's less than or equal to 0.25 by half. So a very common assumption and value that's done in survey samples is you take sigma hat by root n to be roughly square root of 0.25 by n. Okay, so this is a very so you know sigma square by n is roughly 0.25 by n. You simply take a square root and say 0.25 by n square root. Okay, so 95% confidence interval, assuming normal distribution, is 1.96 is that alpha beta value, right? So you multiply by sigma hat by root n, your confidence interval is mu hat minus 1.96 root 0.25 by n, mu hat plus 1.96 0.25 by n. So this guy is your margin of error. So when 95% confidence interval somebody says 3% margin of error, this quantity ended up being 3 for them, okay, in percentage 0.03. Okay, so this is how survey sampling confidence intervals are typically calculated. Of course, there are lots of bells and whistles. Some people add additional factors here. Some additional factors may be added here for correction. Okay, multiplied here. So here and here. So some design factors and all that, so to account for something people introduce, but this is the basic idea. Okay, so let's go back and revisit our survey sampling example. 82% in one study and 40% in another study. N is quite large here, right? So if you go back and compute this, 0.25 by n, n is 3000, n is 9000, 1.96. I mean, you're going to get better confidence interval for the 40% case than 82%, but both confidence intervals have, are going to have very low margin of error, right? So what do you believe? Who do you believe? Okay, so here is where I think you have to look at these two and conclude that the population they were surveying has to have been different. India is a pretty big country, and you have to be very careful who you pick, which segment, etc., etc. So they must have been sampling different segments of the population, because back in November to January, you couldn't have had such a wide variation in number of people willing to take vaccination. So any statistical study, one needs to put out confidence intervals and margin of error, but one needs to look at the overall picture and see if everything makes sense. Okay.